probabilities that this diagram makes a negative contribution. We have to cancel something, and that canceling is an extra probability for producing a positive antiparticle and an electron in the state O when there's a particle present originally in state O. And that phenomenon, that when there's a particle already present, the probability of producing another one is enhanced, is a characteristic of Bose statistics. And that's where it begins. That's to explain to you why it's possible. And if all you have to do is follow more details, more diagrams, more cases, and the whole thing will come pouring out. I've just given an example to show you which direction we're going to go. I'll just do one little example. If we didn't have any particle but started in a vacuum, then you can make a pair Q and P. And the probability to make, you see, you can make pair production, so that makes a particle Q and P. And the probability to make those pairs is sum over all Q and P of this absolute square. And that must be compared to the amplitude to do nothing. And the way that you balance that one is that you have another diagram in which you created a pair and then annihilated it. And if you take minus twice the real part of that, or rather, twice the real part of that is the negative of this. And so that's the way that balances. And the extra diagram we saw on a previous page is extra on top of that. So here's how all the pairs balance. And to finish it all off, what happens is that you find that you have to add all diagrams together. And that you can see the exclusion principle with the positive sign this way. Suppose you had 4 disturbing potentials and you produced 2 electrons with their positrons. And they annihilated again. And now suppose you compared that to what would happen if you produced these 2 pair, but instead of annihilating their own positron, they went across and annihilated the other guy's positron. That would make a figure like this. Well, this is a single loop, you see. And these are 2 loops. And you're supposed to add all the diagrams, so you add this and that, and it'll all fit together. And everybody knows that, and it's very simple, and it makes Bose statistics. Bose statistics, as a matter of fact, is not so very mysterious. As soon as we deal with anything like oscillators, such as the vibrations of a crystal which makes sound waves, we find that those sound waves obey Bose statistics, and we're adding all the amplitudes together. And so we don't find that quite as bad. What we're going to do is we're going to discover later that for each loop, when the spin is a half, each loop gets a minus sign. And therefore, this has 2 minus signs for this 2 loops multiplied together, which is plus, and this is a single loop, which is minus. So when we change to 2 loops to 1 loop, we change from 2 minus signs multiplied to 1, and it's an opposite sign. And you get Fermi statistics. So I'm just focusing now. We have to look and understand why, with spin a half, we're going to understand later why there's a minus sign in the formula for the loops. Okay? Now I'm going to return now, because I have to be more careful, to go a little bit more into detail and to explain the relationship between the antiparticle behavior and the particle behavior. Of course, it's true, and it's still true, that the antiparticle is completely determined by the particle behavior. Let me analyze this a little bit more in detail in the case of spin 0. We noticed that for T2 greater than T1, that is above the plane here, the amplitude to go between 1 and 2 was this integral. I've chosen a special case of scalar couplings and so on because this form is relativistically invariant. The 2EP under the D3P makes a relativistic invariant volume element in momentum and energy. You have to check that someday. This E, energy times time minus momentum times position, is of course the typical relativistic combination of the product of the time components minus the product of the space components. And this is a relativistically invariant form, and I've chosen that one to study. Now, because that plane could have been taken anywhere, we know that all over the outside light cone, if I just tilt the plane, if you want this point here, tilt the plane far enough down, take the coordinate system this way, and you'll get this function. It's always the same function because it's relativistically invariant. So this function is not only true above the plane t equals 0, it's true of the whole negative light outside the back light cone. That is, the space-like region and the future light cone. This formula is right. On the other hand, for t less than t1, and also space-like separated, since energy must be greater than 0 always, we have to have a form that the same amplitude is g21, I mean the amplitude in that region, either t2 less than t1 in the bottom light cone, or else inside with t2 less than t1 but in the space-like region, we'll have to have the opposite sign frequency with a whole lot of weights all added together in some complicated way. The question is, and in the region when T2 and T1 are space-like, we could use either one of these two formulas to obtain the amplitude. It's like a patching, and that makes the functions have to be equal there, and that's going to determine what this function has to be, this G, because we know it's equal F in that region. So the question is, if a T2 and T1 space-like, we have an expression with a negative frequency, can we express it also as a function of positive frequencies alone? Ordinarily, you can't do it. It's magic, but for this particular function, which is relativistically invariant, it's possible. Let me show you why. First, for T2 equal T1, F21 is real, because this isn't here. And when you integrate over P, you have both positive and negative P, and the complex conjugate is just a negative P, so you average both when you integrate, and it's real. F is real. But F is relativistically invariant, and if it was real for the 2 times equal, in another system, the 2 times are equal somewhere else, and so forth, and therefore, since it's relativistically invariant, it must be real for any T2 and T1 which are space-like separated. Fun. Now, since it's real for any T2 and T1 space-like separated, it's equal to its complex conjugate if T2 and T1 is space-like separated. And therefore, one solution is that G is the complex conjugate of F that has the right sign on the frequencies, and that's equal to F in the space-like region. And that's a unique solution, because if I had 2 of them and subtracted them, the difference would be 0 over a finite interval, and I said there's no solution to something with one sign of energy and a difference 0 over a finite interval. So this is extrapolatable out into the times T2 less than T1 in the past light cone, and this is our answer for the amplitude in the past light cone. So here's the answer for the whole amplitude for everywhere. If T2 is above T1 in the forward light cone, it has to be this expression. In the intermediate, where T2 is outside the light cone of T1, it's either this one or that one. They're equal. And for T2 earlier than T1 in the back light cone, this is the right formula. We started by supposing something was relativistically invariant, and they're able to deduce what happens when you go all the way around back on the other side. And that's not so mysterious. Suppose we had 4-dimensional Euclidean geometry. X, Y, Z, and W, all equivalent, so the sum of the squares of all those 4 things was constant. And we start to discuss rotations in that space. That's the analog of relativistic transformations in 4 space, okay? I can invert X, Y, Z, and W by a rotation. Because, for instance, I can rotate in the XY plane and change X to minus X and Y to minus Y. Another allowable operation is to rotate in the ZW plane and change Z to minus Z and W to minus W, see? 4-dimensional. So you can change all of them around. And therefore, once you've supposed the thing is invariant, you know where it is everywhere, even upside down. The only difference in the Minkowski space is that there's a kind of a no man's land where T2 and T1 are outside the light cone, and all the transformations can't really move you through there But we have obtained the correct continuation because the continuity is maintained by supposing that the energies are always positive. That limits the solution. In other words, this operation PT, which changes the sign of everything, is really a relativistic transformation. I should say more correctly, a Lorentz or rotation transformation, kind of. Extended across the mysterious space-like region by the demand that the energy is greater than zero. So it's not mysterious that we can work out the whole function. And it's not mysterious that relativistic invariance produces the whole work. Okay?